Good morning, everybody, and welcome to today. Actually, is election day. I hope that you guys have exercised your basically duty. Okay, and morning. And I see quite a few people who are not here too today, although today is the day after the time change, so I was hoping to see more of the class, but apparently a lot of people got used to the idea of watching the recorded version of these classes, and they are basically doing that. Anyway, excuse me. Today is chapter 19. Today is the last basically chapter into the section that deals with chemistry. In terms of its relevance for what is going to come for us in this class, it's not really that big. But in terms of some of you probably who would want to understand a little bit of how biological system work and other things that are not basically organic matter basically functions and some of the household products, that's probably important. However, like I mentioned before, because of the fact that the next two sections that deal mainly with the earth science and also astronomy, we're going to focus only on probably a couple of items from this chapter as we talk about it, and namely the two hydrocarbons, methane and I think ethane. Those are the two things that we're going to focus on. There is a lot of things in terms of organic chemistry. It's one of the most basically, how should I put it, involved branches of science, especially chemistry, where you have to deal with all kinds of compounds. The key point of this branch of chemistry is the carbon itself. Okay, so that is the main essential ingredient in this whole thing. And after that, there is the combination with other basically atoms, especially hydrogen and then oxygen and other basically elements, and how they combine to find organic matter. Now, it started with organic matter to begin with. That's how this subject started. And then later on developed into not essentially organic matter, but synthetic matter, where basically you can combine carbon in the factory and make with it organic material. So that's basically how this branch of science started. So let's delve into the chapters. I know I post stuff for you guys on Canvas, so I'm hoping that you guys have had a chance to go through it. Excuse me. I hope that everybody went and did his thing, or at least voted by mail. It doesn't matter who you vote for as long as you do. So let me find the file in here. It's this one. Excuse me. So again, the topic of chapter 19 is organic compounds. And for this one, we're going to talk about hydrocarbons, basically hydrogen and carbon, and we will see that you can combine these ones in so many different ways. Excuse me. We're going to distinguish the difference between saturated and unsaturated hydrocarbons. Namely, is all the carbons basically have a single covalent basically connection, a single basically bond between them, or they have more than one. So the difference between the two is how many connections there are, or how many bonds there are between the carbons involved. Excuse me. What makes the organic compounds interesting is actually their functional group, and we're going to talk about that. We're going to go through the main groups and talk a little bit of them. One of the, or at least a bunch of groups are the three of them that are mentioned in here: alcohols, phenols, and ethers. And then you have the amines or alkaloids, which are kind of bases. And then we'll talk about the carbonyl compounds, and there are a group of actually functional groups, a bunch of functional groups in there. And finally, we're going to talk about polymers and monomers and stuff like that. So in terms of importance for us, like I said from the beginning, it's actually the hydrocarbons for what is coming for our chapters. Okay. Okay, so again, organic chemistry is a branch of chemistry involving the study of carbon-containing chemical compounds. Carbon has, first of all, you know that it has 4 covalent electrons. That's what we discovered a long time ago. And that basically makes it combine in too many different ways. So it has so many ways that you can combine carbon with different compounds. Like I said in the beginning, the branch initially started with organic matter, but it does not have to be. I mean, actually, right now in astronomy, for example, we know that hydrocarbons exist outside of the Earth, and they do with abundance. Number one, and number two, not necessarily due to living organisms. So this could be just basically different other processes. So they're abundant because of the fact of how easy it is for carbon to react with other materials and basically form compounds. The main one, as I said before, is hydrogen, and that's why the hydrocarbons in here we start with. So excuse me. So there are a lot of materials, okay, and like I said, there are natural and synthetic. Both of them, they can occur naturally due to living organisms or due to non-living organisms, and also synthetically, where we can actually make them in the laboratory. Again, carbon is so special because it has can connect with another through strong and stable covalent bonds. So that has those 4 electrons, and then it can engage with a lot of bonding with other materials and can be stable and stationary in there. So item number 1 for today's discussion is the fact that this whole thing is based on carbon. So organic chemistry is based on carbon. So the carbon is the most important element of, okay, I'm going to go by Sarah's suggestion. Okay, good for you, Sherry. Glad to hear that. Okay, I hope that the rest of you also do the same thing. Okay, so what is the main element in organic chemistry? That is the question, and the answer, of course, is carbon. And you need to elaborate a little bit more into the fact that it has 4 valence electrons, making it easy to engage in stable chemical bonding with other elements. Okay? Sarah? Yes? Very good. Okay, so that's the item number 1. Again, so this is some examples in here of how carbon basically can connect in here. Of course, you're looking just, for example, I'm looking at this carbon in here. All of its 4 electrons are engaged in bonding in here with different elements. And of course, there are some few that are free in here, and how easy it is for in terms of the energy and the levels of energies involved. For example, the nitrogen is not as strong energetically versus that of a carbon-carbon bond. Okay, the difference is almost twice as much, or actually more than twice as much. Okay, for the oxygen, for example, and sulfur, it's also less. So that's why we said it's a strong bonding in here for the carbon-carbon. So where the carbon can be connected by itself for a bunch of elements, you'll get the strongest element in nature, at least the one that is used for in the industry to cut through rock, and that is diamond. Okay, so that's the point in here that we're trying to illustrate, that it is a stable, strong bonding. That's why you have this whole branch of science is based on how carbon basically connects with itself first of all and other elements in here. So the fact that it connects with another through a strong and stable covalent bonds, that's item number 1. The second point also is that it forms bonds with many other types of atoms. Okay, so this provides almost an infinite number of organic matter compounds. So remember the fact that we're saying organic does not mean necessarily that's a living organism. Yeah, it could be natural, whether organism, living organisms, or non-living organisms. So this could be a signature of life or just no life at all. Okay. In addition to the fact that you can manufacture it in the synthetically. Okay. An important part of organic chemistry are the hydrocarbons, basically hydrogen and carbon. How can you put them together? How many ways can you basically connect hydrogen and carbon? So that's the item number one, okay, that we're going to be focusing on in terms of what comes next in terms of especially when it comes to astronomy. I know this is not an astronomy class, but we're going to talk a little bit about the planetary astronomy. We're going to talk about how, for example, the big giants are their upper atmosphere and how what is it made up of, and also talk about their moons. And you will see that the hydrocarbons there they're present with mass in there. Okay. So again, you have in this case in here, it's the same basically chemical formula, C5H12, C5H12, C5H12. Yet, so you still have 5 carbons and 12 hydrogen atoms forming together different molecules, and they're completely different in terms of their physical properties and their chemical properties, just by the way the atoms are basically rearranged in this case. So you could have it in this form in here. By the way, this is the skeletal form also, which is also another representation, where we assume that in each point in here, in each end of that basically what looks like it's a line, which is the bond, you have a carbon atom. So that's the assumption that we have in here. Because we only have carbon and hydrogen, so what you do in this convention, you place carbon in where the lines join. Of course, you could do it, since we're doing lines, you could draw the whole line like this. But that doesn't make sense. You don't know exactly how many carbons in there. So the convention is you're going to draw it at an angle, and at that point where 2 or more lines meet, you place a carbon in there. So we have a carbon in this convention here, which is this one. You have another carbon in here, which is this one. You have another carbon in here, which is this one. And you have a carbon in here, which is this one. And you have a final last carbon in here, which is this one. So this representation and this representation are equivalent. You ask what happened to the hydrogen. After you tally the carbons where 2 or more lines meet, so there is a carbon in here, and then whatever is missing, you just fill it with the of course, in this representation, this is wrong. I have another one in here, and another one in here, and another one in here, and another one in here. So the ends always will have carbon in them too. So this is, I have a C5, which is exactly this one. Okay, neopentane. But that is one thing. But also the way this carbon atoms basically rearrange themselves will make it completely different compounds in terms of their physical properties, their melting points, in terms of their chemical properties also, and how they bond, and whether or not they dissolve in water or not. So there are a lot of these differences in here. Okay, this is the isopentene again. What you have in this case, it's still you have 5 carbon atoms plus, in this case, 12 hydrogen atoms to form this. So chemically, at least the chemical formula, they're all identical, but the rearrangement in this case will make it you have the different basically compounds. This is called actually a isomers. Okay, so they have the same basically chemical formula, but structurally they are different. Okay, so molecules having the same molecular formula but different structures. So all of these three molecules in this case, they are isomers because structurally they are the same, C5H12, but they are different rearrangements of the atoms in this case, in such a way the structure is different. So they're called structural isomers. So just giving the formula by itself is not helpful in this case. You really need to know exactly how they're arranged. The word probably is not structures, but different configurations, the way that they are arranged. So the configuration in here is a specific way in which the atoms of a molecule are connected to one another. So to go back to the example we were talking about in here, so the way these molecules are connected to one another versus this one's in here, where you have the second carbon, and you always count from the nearest one for functional groups, and we're going to talk about that. So in this case, is connected to another carbon, and in this one in here, there is a central carbon, and all the other carbons are connected with it. So that's what the different configurations you have for this different 3 isomers. So the configuration in here and how the connections are made. Okay, so again, this is not unique to C5H12, but also other compounds. Look at this one in here. 366,319. This could be a question in the exam. Can you write all of the different configurations of this one? You think it's feasible? No, it's not. You're not supposed to remember all of these details, by the way. Okay, just to have an idea, basically, on how there is a pattern in here, how the rules are working, more or less. You don't have to remember all of the details and how they are made up. Okay. Now, in addition to the configurations, you can actually rotate a single, basically, atom around itself, or a single bond itself, and then all of a sudden, now you have a different conformation in this case. You have a different, basically, distribution altogether. And it's still chemically the same, basically, compound, but you have different, basically, reorientations. Case in point in here, if you take this bond in here, or this one, it's the same thing, and rotate it, basically, the molecule will look different. Okay, so this is the new conformations. So this is all of it involved, basically, transformations and symmetries that are involved in this chemical, basically, hydrocarbons. Okay. Of course, the example with it is that you take your arm and basically spin it in such a way, and you have so many joints in here, 1, 2, 3, and actually there is more in here. And as you spin it, you're going to have. So what is that transformation? I forgot what it was, basically, so that you end up with your left hand looking like it's your right, and so on and so forth, okay? So these are two conformations to the same configuration. Again, what is the chemical formula of the following compound? Again, every place in here, I'm going to count, and every node in here, I'm going to count a carbon. So I have 1, 2, 3, 4, 5. Okay, so I have C5, and the only choice in here is C5H12. How could I account for the 12? Well, 12 hydrogens. Since I have a carbon in here connected in here, so I have 1, 2, and 3 carbons. I mean 3 hydrogens. I'm sorry, and I have already 2 of the electrons of this carbon are involved in these 2 bonds. So I still have then 1 hydrogen in here needed and another hydrogen in here needed. So total of 5, because I counted the 3 plus 2. And I have 2 in here. That is 7. Did I count correctly or not? Hold on. Okay, 1, 2, 3, 4, 5. Okay. So I have 1, 2, and 3. That is 6. Okay. Plus 3 here, that is 9, plus 3 in here, that is 12. Yes, so it's C5H. So let's count them again so that the convention is working for us correctly, okay? So we count all the nodes in here and their carbons. So we have 1, 2 carbons, 3 carbons, 4 carbons, 5 carbons. Okay, so that's the convention for the skeletal structure. Now, since there are 2 electrons in here that are engaged with connections, so I need just 2 hydrogen atoms in here, okay? Same thing in here, 2. And the same thing in here, for the same reasons, I have 2 more, okay? In here, I only have 1 electron of this carbon engaged in this connection, so I need 3 more. I need 1, 2, and 3. And in here, same reason, I have 1, 2, and 3. So for a total of how many hydrogens? I have 2, 4, 6, plus 3, that's 9, plus 3, that's 12. So the correct answer is this one. Okay. So for hydrocarbons, it's kind of easy a little bit to find their formula just from the skeletal approach. Again, that's the same with the correct answer. Okay. So in here, just filling basically the blanks that we were talking about. Okay, hydrocarbons basically, because of their the way that they are, basically, you can when you go into the basically into the what do you call it, where crude oil is basically, and dig for it, it comes with different mixtures, different kind of hydrocarbons in it. Because of the way that it is, because the lighter ones basically they boil at a lower temperature than the ones that are actually heavier. So what they do in this case, they increase its temperature until it all liquefies, and then it comes out. The heavier ones, of course, they still liquid, and the others start to evaporate. And then they start to condensate at different levels. They start to basically liquefy at different levels, different temperatures. So the next heavier ones, basically, they are going to condensate in here for a higher temperature, lower temperature than this one, but higher temperatures than the ones above it. And that's basically how you separate, how you distill a different kind of the crude oil, and separate it into different useful kind of versions of the hydrocarbons. At some point, you're going to get gasoline, kerosene, which is used in airplanes, and diesel, which is even heavier and used in diesel engines, and you have lubricants in here, and you have tar. Okay, this one will require even higher temperatures if you wanted to really get it into gas form. And finally, you have the natural gas in here that escapes at the lower end, which can never basically at room temperature be liquefied. Okay, so that's going to stay gas in that form. Okay, so the other rule in here is that there are always 4 bonds for carbon. Now, in a saturated carbon, okay, all 4 bonds now, they're engaged in a single bond with whatever coming in here. For example, hydrogen. This is CH4. Okay, this is methane. Okay, so this one is saturated. For example, carbons are involved when a carbon is involved in more than a single bond. In this case, it's called an unsaturated. So that's the difference between the two. So this is the example for CH4 for the methane. Okay, all 4 valence electrons in here are involved in a single bond, and we have with the hydrogen in this case, and that's how the methane is formed. Now, if multiple bonds are involved, then we're talking, like in this example in here, then this is unsaturated. Okay, so butane in this case, all the carbons, all the 4 electrons of the carbon are involved in a single bond. And as you can see it from this example, C4H10, you have 4 carbons, and again, you have the necessary number for hydrogen to form the rest of the compound. So this is saturated. There is no there is no bond in here with 2 or more. In this example, you have the connection, and this is also C4, except now you're missing 2 hydrogen atoms, so the carbon in here in this case is forced to form a connection between itself. Now this is unsaturated, and unsaturated because of this fact. Okay, the convention naming in here for hydrocarbons, actually for all organic matter in here, there is a convention that we're not going to go into details about it. And basically you start counting from the nearest where this function or this functional group occur, and that is the starting point. Doesn't matter if you start in here or in here. Okay, they are symmetrical. But then the next one is going to be the next carbon atom where this group occurs, and that is the number 2. That is what you see in here too. And this is not an alkane, this is an alkene, and we're going to see the difference between them. Okay, so the naming in here also matters. So that's why it's called the butene versus this one is butane. Okay, we have a special case of this, which are called the benzene rings, where they form actually more than, I mean, they have multiple bonds in this case. The trouble with it in this situation is that it forms a ring, just like this one, and the bond actually is not, because of the symmetry in this case, it's not necessarily fixed with the two carbons in it. Actually, it floats in here because of this symmetry, because of this rotational symmetry. So that's why we use this representation, that actually the chemical bond in here, it goes around, actually. It moves around, floats, actually. So it's right now, it's in here. Next time it's going, this one will move there, and the other one moves accordingly, and the third one moves accordingly until, and they don't stay stationary in this case. So the valence electrons in here that form the second bond in here, they're not in a stationary position. They move around. That's why you see sometimes the benzene in this case is formed into this ring in here, okay? So again, this is, I mean, it's formed into a circle, what looks like it's a circle. It's just to indicate the fact that this bond is not fixed between two specific carbons, and actually moves around and rotates, okay? So again, these are the benzene rings, and you have different kinds of materials in here, okay? Again, I'm just going to go briefly on this naming convention here, what the 1,4, and you will see that in organic chemistry a lot, okay? Sometimes this number is preceding the actual group in here. So you look at the functional group. In this case, you have the chlorine added to this element, and here they are, okay? Because this is a cyclic molecule, so where are you going to start from? You don't have specific, so you have to start usually from the nearest functional group, which is, let's say, for example, it's this one, okay? So we have 1 in here, okay? And then you start counting. You have 2, you have 3, and you have the 4th one in here. So that is what the 1,4 means, okay? The functional group. And what you have in this case, you have a di, chloro, that's chlorine in this case, benzene, because it's that ring of the 4 carbons in here, the 5 carbons in this case, okay? So again, sorry, 6, what am I talking about, okay? For this structure in this case. But that's just the naming. But the point in here that I'm trying to say in this case, that they are all making these connections in here, and they're an example of an unsaturated, non-saturated, basically hydrocarbon. Obviously, this is not necessarily because it involves not just the hydrogen and the carbon. So this is because of that. It's really slightly different than what we've been talking about in here. But this one is pure hydrocarbon, and so is this one. Okay. Okay. How many carbons in here we have? We have 1. We have 2, 3, 4, 5, 6, 7. So this is a C7. And how many hydrogens we have in here? We have 3 connections, so I need 1, 2, 3, 4, 5, 6. Okay, plus 3 here. Should be 9, H9. Okay, again, a normal benzene by itself is going to be C6H6, but I am added in here another carbon, so it becomes C7, and that carbon is only involved with a single connection by itself in here. So I needed to add the 3 necessary hydrogen atoms in this case to form the H9 in this case, okay? Oh, I'm sorry, did I? No, I think I have made a mistake. This is an 8, okay? This is an 8 because this one is already accounted for, okay? So this things in here need to be corrected quickly. Okay. Let's look at the same example as before, except now we have this covalent bond in here. That means that this carbon in here has already 1, 2, and 3 of its electrons engaged. So the only number of hydrogens I need in here is 1. Okay. Same thing for this one. It has 1, 2, and 3. So the only number of hydrogen in here I will need is 1. However, this one still needs 2. Okay, because only 2 of its valence electrons are involved. So I need to compensate for that. And here, of course, I need 3 of them. Same thing in here. So what is the formula for this one? I still have 1, 2, 3, 4, 5 carbons. How many hydrogens I need in here? I need 3, of course, in here, plus 2 in here, plus 1 and 1, plus 3. So total is 3 plus 3, that's 6, plus 4, that should be 10. Okay. Does this make sense to you guys? And how to find the formula based on the skeletal representation of the molecule? Yes or no? Come on, guys. Okay. Okay, let's go through the same example in here, because I don't want, I'm gonna have some of you have some doubts, and you're entitled to an understanding, of course. So again, this is just a representation of the molecule. There are different representations, and the one that we have actually is also another representation. So this one, what it tells you, the rule is, in every node of any line, you have to place a carbon in here. Okay. One line in this case, or more than one line meet, you have to place a line. Okay. What this means in here, for this line in here, is that you have 1 electron is engaged already in a connection. So you're missing 3 in here. So 3 needs to be connected. Okay. However, in this example, in here, I already have 1 valence electron involved. Okay, because these are carbons now. So this is C, this is C, this is C, this is C, and this is C. So I'm counting 1, 2, 3, 4, 5 carbons. So it puts me under either this one or that one. So I know these are not correct. Okay. So if I'm given a choice, these are completely wrong, because I only have 1, 2, 3, 4, 5. I excluded 2 answers already. C and D are not correct. So the question is either A or B. Okay. I need to find now the number of hydrogens. The first thing you really look at in terms of here is the multiple bonds you have in this case. You have 2 between these 2 carbons. That means 2 of their electrons, each one of them are already involved in those double bonding. So you're left only with 2. But one of the 2 is actually here too for this carbon atom. So you're actually left with 1 only. So only you need 1 hydrogen atom in here. Same thing for this carbon atom. 2 of its electrons are engaged in this double bond in here. So 2 of them are accounted for. Now, the third one is actually involved with this carbon, so 3 of them are accounted for. So you're missing 1, and here it is. Okay, so that is the one that you are missing. So you need to add a hydrogen in there to compensate for the third one. I mean the fourth one. Okay, so when you're done with the double bond. Now you go to the rest of them, which are easy. This carbon in here has 2 of its electrons engaged, so you need 2 to make up for the other 2. This carbons at the end only have 1 electron engaged, so you need 3 hydrogen atoms to account for the missing connections for the 3 electrons. So you need 1, 2, and 3. 1, 2, and 3. And now you start counting. Okay, I have 3 here. And I have 3 here. That's 6. Okay, I have 2 here. That's 8. And I only have 2 left in here. That is 10. So which put me, this is the correct answer. Is it better now? Okay, good. How about you, Sarah? Okay. How about Sarah? I'm glad that more people are joining me. Gonna make sure that everybody else also. Okay, guys, it's really is. If you have still having doubt with it, do a little bit more examples, and it should. Okay, good. I'm glad to hear that. Okay. So again, this is the answer to it. So that's basically, again, this is just a schematic of what I was trying to say in here. So we're going to skip through these things in here. Okay, what is a heteroatom? It's anything other than carbon and hydrogen. I mean, yeah, other than carbon and hydrogen. Like oxygen, for example. Anything else added to it, now it's already too many with the hydrocarbons. That's how many elements you can have. Add to it oxygen or nitrogen or other or chlorine or something else, and now the whole thing can explode in numbers. Okay, so a heteroatom is any other thing other than these two. Okay, other than the hydrogen and carbon, which are essential for the hydrocarbons. Okay. But now what we do in this case, we group them in functional groups. So basically, if there is an oxygen and it forms a bond with the hydrogen in this case, you have an OH group in this case, which is an OL group when we're naming these things, which is the alcohols. Okay, so you have different groups. From this point on, basically, we're going to just talk about some functional groups, and after that, we're going to basically put a summary for this thing. So again, organic molecules are classified by the functional groups they contain. So what is a functional group? Is that there is similarity in their chemical properties and sometimes even their physical properties, and they're put together based on those properties. Okay. So here is a table. I know I did not include this part of this slide in your PowerPoint, but this is straight out of the book. Okay, so this is a table that summarizes everything that is coming next. For the vast majority of the chapter, it's just summarized in table 19.1. Okay, where do I find the summary of all functional groups, which basically gives you everything in here? The answer in this table. Okay, so if that is the second point for the discussion, everybody. Okay, and per Sarah's request, I'm having it in here too, so that you guys can see it. So I did not include that in the initial basically PowerPoint presentations, but I don't remember exactly what page it is, but it is table 19.1. It gives you a summary of all the functional groups. Okay, alcohols. Okay, alcohols, they are characterized by the presence. Let me make this one slightly less to make this page. Can I make it bigger? No. F5 maybe. Oh no, escape. Okay, get me back to the original page where I started from. That is because it's my fault. Okay. Anyway, I was trying to have you guys look at this, and if you guys have the book ready with you, you can look at this table in here. It summarizes all of the functional groups as I was talking about. So you have the hydroxyl group in this case. This is basically the hydroxyl group that you're looking at in this case, COH in this form. If you see it in any kind of a molecule, whether nothing attached just by other hydrocarbons or other groups involved, you know that there is this function that molecule plays, and that is an alcohol. And you add, when you're naming to it, you add an OL toward the end in here. Okay. Okay. Then you have the phenols, which looks similar to it, except now the carbon in here is actually you have a ring in here in this structure in here, similar to the benzenes. Okay, so you have a benzene with an OH attached to it. Okay, so in this case you have a phenol group. Ethers, they're characterized by this structure. You have an oxygen that is bound to two groups of carbon-based, basically groups in this case. Usually the representation for it in other textbooks is O, R, and R prime, and an R and R prime is the rest of the molecule basically, and the other kind of rest that is not necessarily the same. Okay, so these are ethers. Originally they were used in terms of the in medicine for to make patients basically go to sleep. What is that word used? I forgot the I'm not a biologist, by the way, or anywhere near where people are in. I lost the word right now. Okay. Okay, and you guys are not helping much. I know some of you work in the health industry, and they should know these things. Anyway, you have the amine group, which are also characterized by this basically group that you will find it. If you find it, you know that that's a function. Ketones, like the acetone, they have this group in here, which is this carbon in a double bond with an oxygen. Remember, the oxygen has 2 valence electrons. So that's why you have H2O, because both of its electrons are involved with the hydrogen separately. But in this case, both of the valence electrons of the oxygen are involved with the connection with the carbon, which frees up the other 2 basically carbon valence electrons to connect with different groups basically of carbon-based atoms. So in this case, you have the acetone used for nail removers. No, what do you do? Yeah. Okay, then you have the aldehydes, which is another group by itself. Again, you have, instead of in here, have a carbon group. I have actually hydrogen, and it's similar in look to this one. Okay, and then the amides in here, instead of hydrogen, you have a nitrogen, and nitrogen have 3 valence electrons, so you have to have 2 more involved with other kind of group connections. And then you have the carboxylic acids, which you involve with this basically group. And then esters, okay? So you have all kinds, these are the main 5 functional groups in organic chemistry. For us, we're going to probably remember a few of them, but as I said, we already hit on the main things in terms of what we do in chemistry, what we do for the rest of this class, okay? So the first groups, I mean, some of the groups that we can look at in here, you have the ethane, okay? This is just a pure hydrocarbon in this case, okay? And then you have in this case, you have ethanol, where we basically, instead of the carbon connected directly to a hydrogen atom, in this case, it's connected to an OH in this case, okay? Because remember, the oxygen has also 1 valence, so you remove this one, and then because of the presence of the OH, which makes it into an alcohol, then you have the naming has changed to ethanol. So you still have C2 in this case, H6, C2H6 still, but you have an oxygen in here. So it's C2H5OH, okay? So that's really because the OH needs to be grouped into a functional group, and here is a group OH in this case, okay? And then you have another possibility for it, where you have the nitrogen in this case, in this group, which is the amine group, connected with the carbon, except in this case, you have the carbon group, which is, in this case, you have the ethyl group, which is, you have C2H5, still, C2H5 and C2H5 with the hydrogen become just a normal hydrocarbon. Now, in the presence of oxygen, it makes it into an ethanol because of the OH group. But now you have an NH3 in this case, which makes it an enthalmine, which is this kind of group. So you have different ways of making basically changing just the same original base and changing it to different molecules with different physical properties and different chemical properties. Okay. In which of these groups following structures is carbon bonded to 5 atoms? Okay, you have a carbon in here. Okay, let's see here. Is D, we have a carbon bonded? No. Let's see here. We have a, you mean this one, probably, Sarah. Okay. So I have 1 connection in here, 1 bond in here. There's another one in here, and there is another one in here, and there is another one in here, okay? This oxygen has one of its valence electrons with this group, and another one on this side, okay? So this oxygen is already full. I mean, all of its electrons are, or valence electrons are engaged into connections. The carbon in here that is sitting in this node has only 4 of them. So same thing, carbon in here has actually 1, 2, and probably 2 in here, okay? And the same thing with this one. So I don't see any one of them in here. Does this make sense? Okay, good. So okay, carbon can never be bounded 5 times in none of this above, because carbon basically has only 4 valence electrons, okay? So that's it. So in which of the following structure is carbon bounded 5 times? Can we do that? Let's see here. Let's count them. I have 1, 2, 3, 4, and 5. Does this make sense? Does this molecule make sense? Didn't we just say that this is not possible? You have 4 valence electrons, so how could you end up with 5 covalent bonds in here for that carbon that is sitting right in here? I mean, well, there is no problem with the rest of them, okay? A, B, and D, they are no problem. You guys understand that? Yes? But it seems that there is a matter with C. So first of all, it's showing me 5 bonds, okay? It's showing me that somehow this carbon is making 5 bonds. So how is it going to do that? Since it only have 4 valence electrons. What does this mean about C? What do you guys think? In other words, is this really a real molecule, or is there a mistake with it? So that's the question. Because it's showing carbon involved with 2 bonds with an oxygen in here, involved with another bond in here, involved with another bond in here, and involved with another bond in here, for a total of 5 bonds. I know it only has 4 electrons, 4 valence electrons. So is this possible? What do you guys think? Or is this nonsense? Come on, guys. I don't understand, Rudy. What do you mean by no? Is it possible? No, you're saying it's not possible, that this is no good. Is that what you're saying? Okay. This is confusing, Rudy. I need a clear answer. You're sounding like a politician.
No, it's not like possible for it to have.
I think I know where you're headed, but it's kind of a yes, it's not possible. That's confusing a little bit. So yes, you're right. Okay. Okay. Yes. So you're right. Okay. So it's not possible. I mean, that's not really. I mean, this is a mistake, clearly. Okay. Is everybody good with that? By the way, if you do something like this in an exam, it might not count, okay? So if you say no, yes, no, that might confuse me, and I would be like, what is he saying, yes or no? So, okay? So, like I said before, this is not a democracy. When we vote, it has to be this or that. We can't really. Okay. So, although I know exactly what you mean in here. Okay. So this groups in here because of this hydroxyl group. First of all, the alcohols. Okay. Because they have this OH group in here, they become what is known as a hydroxyl group. So in this case, you have the COH, and the carbon in this case has 3 of its valence electrons connected with 3 different, basically, other things. Okay. For example, methanol, which boils at, what is it, 65 degrees, has CH3OH. So that's the chemical representation for the methanol. You try to leave the functional group by itself. Okay, I know you might be tempted saying it's, what is it, COH4. That's not how you represent it. CH3OH. Okay, again, just to emphasize the fact that you have the functional group in here. Okay, in addition to that, you have ethanol. Okay. Methanol, by the way, I think it's not good for consumption, but it's also an alcohol. Okay, it's actually toxic. Ethanol, which is actually used for because of its properties, is actually using gasoline to improve to improve its octane content. Has this chemical property. So this is the difference between the methanol and ethanol. Again, it's a methane basically based. Okay. Methane based if I don't have this OH group. So when you add to it the group OH, it becomes methanol. Okay. Same thing with the ethane, which is normally C2H. What is it? 6 in this case. C2H6. But you remove one of them, hydrogens, and it becomes ethanol. Okay, so this is the boiling point for it, 78 degrees. The 2-propanol, okay, in this case, again, the number 2 in this case, and I already mentioned that in the beginning, it has to do where the functional group is. Okay, the functional group in here, you usually start from the nearest end. Since it's really sitting in the center, it doesn't matter where you start from. So you start to the right or to the left. So you start counting 1. So where is the functional group in here? In this case, it occurs in the second carbon atom. So in this case, it's the 2. That's where the 2 is. If you said, no, I don't want to start from here, I want to start from here. In this case, it doesn't matter. Okay. But if you start, for example, when it's 3 of them, and you start from 1 and then 2, and you find their group in here, so that's the name you stick with. You don't go from the other end, 1, 2, and then you find 3, because the shortest in this case would be 2. That is a different example than this one, but for this example, it is only one way, whether you look at it one way or the other. And again, the group in this case is the all. Okay. And it's propane, C2, C3, H8. What is it? Yes, it's H. But one of them is gone and is replaced by the OH. So in this case, you have 1, 2, 3, 4, 5, 6, 7. So it's a C3H7 OH. Okay. So that is the 2-propanol. Again, its boiling point is here. So they have different physical properties. Okay. So that is the OH group or alcohols. Phenols, again, this is a different group. This is the second group where you have, in this case, this benzene plus the OH in it. Okay, so this is a different group in here. When you find it, it's going to have a different properties. Again, phenols are acidic because they react with the hydrogen in this case, with the water in this case, or with the other molecules, and you can actually lose their hydrogen, and they become just like another acid that you have in this in other places. Okay. Again, this is just a representation of how they lose their oxygen in this case, and where you can place the negative charge in this case. Okay. This is a different kind of phenols. And then finally, you have the ether group. The ether group is characterized by the presence of an oxygen, and on each side there is actually a carbon group in here in this case. So this is the rest of everything. So that's why sometimes in the literature they're presented by R and R, ROR. Okay. And they're not necessarily the same groups in here. So that's why in some other literature you have to distinguish between the two and put a prime on the second one. Okay. So this is the dimethyl ether. Okay, again, it's an ether because of this oxygen in here. Okay, some of these names sometimes they don't follow the conventions because they were given before the convention was adopted in the early 1900s. Okay, and in this case, again, you have 2 carbons in here, which is the ethane again that we talked about, but it's actually an ether because of this oxygen present in here with the 2 groups, which happen to be the same basically carbon-based structures, but they are on the 2 different sides of the carbon, the oxygen in this case. Okay. So again, this is the comparison with the ethanol. So now this is a diethyl ether. Again, you have similar groups in this case, which is the C2H5. Remember, C2H6 is your ethane, okay? But the C2H5 in here, that is the ethyl group, but you have 2 of them, okay? And you have the ether structure because of the presence of the oxygen between them. In terms of the 4th group that we're going to be looking at, this is actually the wrong title in here. This is the amines, which is part of the, okay, again, the table in here so that you guys are back into with me in here. We are here at this point, okay? So we explored 3 of these functional groups. Now we're actually in the 4th group of this table in here. So the amines, and they are basically base-based. Okay, they behave like bases, like not acids. Again, this is because nitrogen usually have 3 valence electrons, so 2 of its electrons are already tied up. And the last groups are actually the carbonyl groups. Again, they are different groups on the table. Okay, the main things in here, and that is the acetone, is an example of that. So this is the ketone. That's the 4th or the 5th actually in that table. Okay, and then you have the oh man, I can't even say these things. After they become so many of them, I don't know. Okay, so that's another group. Okay, you're not supposed to memorize these names, by the way. Okay, acetaldehyde. Okay, and this is the acetone. Okay, the normal acetone. In other words, you can combine actually different functions too. Okay. Okay, let's see here. This is the one that is used to kill mosquitoes. See where we can get into the main points in here. What time? We still have about 10-15 minutes. Okay, polymers is another. So this is the functional groups. The one to remember. Actually, the main things are the first few groups. Again, for our purpose, like I said, we are done with the hydrocarbons. That's the main thing for us, at least for our class, for the next few chapters. And the others, I would leave them for you guys to go and learn more about them, especially in terms if you're going to get into very much organic chemistry, the namings, and it's really very, I mean, you cannot do it fair justice just with one lecture, okay? So it's a long topic in here and how to name them, and okay. So again, Polymers are a very long organic molecules made up joining together a smaller group of molecules known as monomers. So you take a monomer and you connect it more and more and you end up with a polymer, okay? Like in this case in here. Polymers are used extensively in industry. Like for example, you have the ethylene in here. So what you do in this case, you break the carbon in here and now you have all of a sudden possibility to join them. And now you're going to form an ethylene polymer just by connecting them, moving the electrons to the other side. And now all of a sudden, you have a repeating chain of CH2, 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 and that can go for thousands, basically, of repetition of this monomer. Okay, so it can be very, very long molecules. So that's why they are. Okay, so now this is how you end up with this structure. Okay. So remember, you started with ethylene, and then all of a sudden, you made it into very long. So what is the monomer in this case? Is CH2. Okay. No, I'm sorry, it's the C2H4. Okay. So again, the C2H4 is your monomer, and it keeps on repeating and repeating forever and ever. Okay. Same thing with the what is it, propylene. Okay, so the same thing, you can form a polymer just by breaking those bonds between the carbons, and now you connect them together, and now you have a very long chain. Okay, I don't really expect you guys to delve into this. First of all, there are 140 slides. A lot of them are just basically showing you the different steps on how to form things and how to move things around. What is the main thing for us in this case in here is the fact that organic chemistry is carbon-based. That's the main element in here for it. Carbon has 4 valence electrons. Okay, that's why that question earlier was not possible. Okay, and you can form the first kind of basically organic matter that we talked about is hydrocarbons. Organic matter, I use the word organic chemistry, organic compounds, but they don't necessarily mean that they are formed naturally in organic materials necessarily. They can be actually formed whether through living or non-living organisms or non-living structures. And then the second thing in here is that actually they can be made in the industry, and there was a big revolution when we started to make them and make them into synthetic materials. Hydrocarbons, they involve only hydrogen and oxygen, okay? And we have 2 main types, actually. You have the alkanes and the alkenes. The difference between them is actually one of them is saturated, namely the alkanes. The alkenes are not saturated, they're unsaturated. Unsaturated or not saturated in here indicates into how many bonds are the carbon involved with. If all of their electrons are involved only with this basically single bond with the different materials, they're so-called, they're saturated. If not, they are unsaturated. And then we get into a little bit more into organic chemistry, but I did not really feel like we should really delve into it too much, and that is the functional group, because it can be very, very, very long and very tedious, and a lot of issues basically that you have to explore, and different one of them. The main groups we explored in this class are actually the alcohol, okay, which has that characteristic with the COH, basically carbon group on one side and OH on the other side, and the main thing actually is the OH, because the carbon is always involved anyway. And then we have one with the benzene basically in the OH, and then we have the ether, and we did not really go into much detail later on with the ketones and other thing groups. But that's basically some of the functional groups, and that's the word to remember in this case, just the groups in here. I don't think that this questions from this chapter will be very much basically other than what I mentioned in terms of hydrocarbons. So in an exam environment, you're not going to get into different functional groups for this class, because we're going to get into the hydrocarbons for sure, because I need them later on. And that is in a nutshell what this chapter is all about. Any questions? Recording.
So there's only like 2 questions for this, correct?
Yes, there was only 2 questions today.
And then what was the first question again?
What is the main element in organic chemistry?
Okay. Thank you.
And please don't give me a short answer in the sense that this is only carbon, because that's the answer to it. I need to know its properties and what makes it so important, and the fact that it has 4 valence electrons and can combine in different variety of combinations, and basically with different with hydrogen and also non-hydrogen atoms.
Gotcha.
Heteroatom. Okay.
Mhm.
No. So I'm going to stop the recording.